So I can start. Good afternoon, everybody. First of all, I would like to thank you, Stelios, and all the people involved in the HARMONIA COST for the invitation to participate in this interesting workshop. My name is Antonis Gkikas. I am an assistant researcher here at the Academy of Athens, and the topic of my talk is related with the dust climatology from spaceborne remote sensing observations. Here, Here is how my talk is structured. I will start with a short introduction, then I will move to the description of the MIDAS dataset, which has been developed and which has been used in order to perform an analysis for the global and regional dust climatologies. An analysis also has been performed for the global and regional dust trends. Other researchers have also used this dataset. I will show you some examples, and I will conclude with a MIDAS upgrade and some upcoming activities. No. Okay, it doesn't work. So I will use this. So here is an overview of the role of dust within the Earth atmospheric system. This is a leaflet from the InDust, and you can see that we have the dust emission from the desert, arid areas under the impact of strong winds. The dust is uplifted in the atmosphere and interacts either directly with the incoming and the outgoing solar radiation, but can perturb the Earth radiation budget indirectly by modifying the cloud properties. Dust is also can affect infrastructures, several anthropogenic activities, is transported over urban areas, it can affect the air quality and can cause health effects. And upon its deposition in solar panels, has impact on the solar energy production. Upon its deposition on the ocean, has impact on the fertilization of the seawaters, and also when deposits over snow and ice-covered areas can modify the albedo there and can accelerate the melting of the snow and the ice. From a global perspective, the main global dust pattern, besides with the well-known dust belt stretching from the western parts of the Sahara to the eastern Asia, as it can be shown here in Sao Tal, based on meteorological observations. What you see here is the global dust weather frequency, but dust is not only limited near the sources, it's affected at various distances and at various directions based on the prevailing atmospheric circulation, as indicated here in the most important transport pathways worldwide, in the northern hemisphere and the southern hemisphere. So dust is widespread, covers vast areas of the planet, and for this reason, the satellite observations are a unique tool towards monitoring the evolution of the dust plumes. For this reason, they have been deployed several techniques. Here you can see the LIVAS Calypso dataset relying on active remote sensing retrievals, where you can have vertically resolved observations about the aerosol optical properties and the macrophysical properties. There are synergies between passive spaceborne retrievals and model outputs. We have the thermal wavelengths at 10 micrometers. Here's an example from IASI. And of course, we have the geostationary satellites, which providing us observations every 15 minutes, which is very important because we can monitor the evolution of the dust plumes. But today we are going to discuss about MIDAS. The full name is Modest Dust Aerosol. Sorry. Sorry. Okay, so we are going to discuss about MIDAS, which has been developed through the synergy of passive spaceborne retrievals and reanalysis products, provides columnar dust optical depth at 550 nanometer along with the associated uncertainty. We have global coverage at fine spatial resolution, and the data are available on a daily basis for the 70-year period spanning from 2003 to 2017. Talking about MIDAS, probably you have heard about the King MIDAS. in the ancient Phrygia, in the Minor Asia, in the central Turkey, who was famous for turning into gold whatever he was touching. Actually, there is a measure of success. Someone, he has or she has the Midas touch. But this is not always good, because as you can see here from the illustration by Walter Kane, Midas has turned into a gold statue, his daughter, after touching her. All the results that I'm going to present you today have been already published in these 3 publications, and also there is a webinar in the INDUS where you can visit the relevant tab in the INDUS webpage. And I will start with the Midas development. Here is an overview of the applied methodology. We are starting with the MODIS Aqua AOD. We are using the MERA2 dust fraction in order to calculate the dust AOD from the total AOD. But before using, we are using the Livas dust fraction. This is model and this is observation. And we are using in order to evaluate the performance of the MERA2. And finally, we have the Midas dust AOD. In this chain of processes, there are main critical points, such as the derivation of the Midas DOD, the evaluation of the MDF versus the LDF, and the evaluation of the final product against Aeronet and the comparison against MERA2 and Livas. I'm going to discuss only these 2 for brevity reasons. And for the derivation of the Midas dataset, we have used the MERA2 reanalysis products and spaceborne observation from MODIS Aqua. And these are the 2 simple and straightforward formulas which are used in order to calculate the contribution of dust AOD to the total AOD based on MERA. And then we are using this fraction in order to derive the MODIS dust AOD from the MODIS AOD level 2 retrievals. So we have fine spatial resolution. Here is the Aeronet data that we have used in order to evaluate our product. And this is the way how we are deriving the AOD. We are keeping only records when simultaneously the Aeronet angstrom exponent is lower than 0.75, and the difference for the signal scattering albedo at these 2 wavelengths becomes positive. This is made because we know from Gkikas et al. In 2012, I'm talking for the signal scattering albedo, that the decreasing absorptivity for increasing wavelengths in the visible spectrum is observed during pure or dust-rich environments. Then from the coarse AODs, we are calculating the angstrom exponent in order to obtain the coarse AOD at 550 nanometers, which is considered as the Aeronet-derived dust AOD. And based on this approach, we have a mitigation of non-dust aerosol's contribution to the total aerosol load, but at the same time, we are ignoring the fine part of the portion of the dust particles to the total dust load. Based on our criteria, we have data from 436 stations, and these are the overall scatter plots where you can see that we have a very good agreement between the Midas dust AOD and the Aeronet dust AOD. The same analysis has been performed at the station level. We are selecting sites with at least 30 matchups between ground-based and spaceborne observations. These are the results for the number of observations, the correlation coefficient, the root mean square error, and the bias, where you can see that we have very high correlations over sources and downwind regions. The maximum root mean square error levels are observed in the sub-Sahel. And we are finding mainly positive biases in the main dust sources of the planet, but please keep in mind that we are ignoring the portion of the fine particles to the total dust load. Then we have compared Midas against the model values from the MERA2 and from the observed values from the Livas dataset. As you can see, qualitatively there is a good agreement in terms of pattern, but there are deviations, declinations as it concerns the magnitude of dust AOD. All these are discussed in the paper. And here are the results for the intra-annual variation for the whole globe and for both hemispheres, where you can see the maximum declinations among the 3 datasets are observed during boreal spring for the whole globe and for the northern hemisphere. After evaluating our dataset and comparing with other datasets, now we are taking into advantage the full dataset. And we have reproduced here is an example of the long-term average value at the global scale. These are the average uncertainty, and this is the availability. And you can see that we have the maximum dust AODs up to 1.2 in the bodily depression, which is the most active dust source worldwide. We have moderate to high DODs in the Western Sahara, in the Middle East, and the Taklamakan Desert. We have the signals of transport over the Pacific Ocean, and the most dominant is over the tropical Atlantic Ocean. Here are the average uncertainties are scaled with dust AOD, and the Midas dust AOD availability is higher than 70% over areas less affected by clouds. The same plots, but on a seasonal basis, are presented here. There is a lot of information here. I'm not going to discuss in detail what you see here because the time is very limited. I will highlight only the most important. You can see that the bodily depression is always active throughout the year. We have the activation of the dust sources in spring and mainly in summer in the Western Sahara under the impact of the Saharan heat low. Under the impact of the summer winds, we have stronger dust loads in the Middle East. Within the course of the year, the maximum values for the Taklamakan Desert are recorded in spring. We have the transport mainly in spring from the Asian dust towards the western coast of United States. And the most dominant pattern is along the tropical Atlantic Ocean, where you can see that within the course of the year, there is a migration from southern to northern latitude, and also the maximum rains and intensities are recorded during summer when the dust particles arrive in the Caribbean Sea. Based on the MIDAS dataset, we have performed an analysis related to dust climatology. We are focusing on dust sources in downwind areas, and this is an example that I like very much because it shows why it's important to have fine data at fine spatial resolution. For example, here in Mesopotamia and Middle East, you can see the patterns, the details. Also in the Saudi Desert, in Ad-Dana in Saudi Arabia, and the Rub al-Khali, the southern part of Saudi Arabia. Here is the dust area, the desert in Oman. And in the Red Sea, in the southern sector of the Red Sea, you can see the patterns of transport of dust transported either from the Sahara or from the Middle East. And in Australia, you can see the signal from the Lake Erie Basin. This has been repeated. This analysis has been performed for 9 regions, hosting the major sources and areas subjected to dust transport. Moreover, we have selected 17 areas. I'm not going to discuss all of them. We'll focus only on the Mediterranean, where you can see the interannual time series of the total AOD with black, of the dust optical depth with red, and the ratio of dust AOD to AOD ratio, dust AOD to AOD. In the Mediterranean, we have the stronger loads and the higher dust contribution to the total AOD in spring, mainly in the central and eastern parts of the basin. Here is the same analysis, but now we are looking at the whole globe and the 2 hemispheres. In the upper panel are presented the interannual time series. In the bottom panel, the interannual variability. And you can see that we have significant contribution of dust AOD for the whole globe and in the northern hemisphere. We have weak dust loads in the southern hemisphere. And within the course of the year, for the whole globe, the maximum AODs can reach up to 0.05 and the contribution up to 33%. These values are getting higher when we are focusing on the northern hemisphere, and they are becoming very lower when we are focusing on the southern hemisphere. And the climatological values, this is the climatological value for the whole globe, 0.032, which is in a very good agreement with previous studies. It is almost the double value for the northern hemisphere and very low in the southern hemisphere. An analysis also has been performed about the global and regional dust trends. These are the results using the default spatial resolution of the MIDAS dataset, and after grading at the coarser spatial resolution at 1 by 1 degree. Actually, what you see here is the calculation of the trends of the calculation of the monthly arithmetic mean and geometric means of the dust AOD. We are calculating the trends of the deseasonalized dust AODs. These are the criteria, and we are presenting only the results when we have a statistical significance at 95% confidence level. The maximum positive trends are observed in the western parts of the Sahara, and the maximum negative trends are observed in the bodily depression and in the Thar Desert. And currently we are working to analyze the factors which contribute to these trends. Based on the global maps, we have defined 9 areas, 9 regions, and we are calculating now the regional dust trends for these regions of interest. For these 9 regions of interest, what you see here in the x-axis is the starting year from 2003 to 2013, and in the y-axis you can see the duration of the trend expressed in number of years. Based on this illustration, we can find if there are changes on the sign. Here is an example in North Arabian Peninsula. Again, I'm not going to discuss all the details here, but only for the Mediterranean you can see that we have the predominance of negative trends, and in most of the combinations, these trends are statistically significant as indicated by the hatched bars. The MIDAS dataset has been used also from other researchers for other applications. I'm going to use some results. This is a work from Elias, who's sitting here, who used MIDAS in order to calculate the perturbation of the GHI and the DNI irradiance for the broader area of Cyprus. We have the work from Kyriaki, who utilized MIDAS. Sorry, it's. We utilized MIDAS to evaluate the performance of the CAMS model and also to calculate the change of the annual GHI based on the MIDAS and the dust AOD and the CAMS dust AOD. MIDAS has been used for evaluation purposes. These are some of the results of the studies. There are more. Here is the REMIF with the IFS, and this is a work in the framework of the ISA Newton project, where Vasilis presented some results with the Aeolus wind data simulation. Here is the WRF model for the period in October 2020. The shaded areas correspond to the difference between the model AOD and the MIDAS dust AOD. When the model is initialized without taking into account the Aeolus wind simulation, and the bottom panel when the model is initialized after taking into account the Aeolus wind profile simulation. And you can see here that there is a significant improvement with respect to MIDAS. Some of our ideas, this is the work from Di Tommaso et al. In 2017, who assimilated MODIS observations from deep blue and dark target in the Monarch model, and she demonstrated that there is an improvement of the model performance when we are assimilating these values. So the idea is that if the MIDAS can give us better results. This is a description of our short experiments that we have performed based on the Monarch model. We are using different data sets for the initial and boundary conditions, different emission schemes, and random perturbation of the emission dust size distribution at sources and friction velocity thresholds. These are the results only for January 2012. These are the first guess, the analysis, and the difference between these two, where we can see that there is a response from the model. And based on the evaluation, we have better evaluation metrics for the analysis compared to the first guess, and this is attributed to the simulation of the MIDAS dataset. This is a new study led by Stavros Solomos, who is implementing a new dust mineralogy, the WRF model. What you see here is the percentage of quartz in clay soil and the percentage of iron in the arid soils. This is a very new development in the WRF model, and now we will compare the outputs for the AOD that the modelers will produce will be compared against MIDAS. And as it concerns the upgrade, currently we are working on the temporal expansion until the end of 2022. In parallel, we are processing the MODIS Terra retrievals. We are starting an analysis related to dust trends in the Mediterranean to highlight the governing processes, to see if the CMIP6 models can reproduce these processes, and then to decide which of these models can be used in order to have future projections for the 21st century. And of course, it is always our priority to perform assimilation experiments. This is what we have done with MIDAS, not only us, also other researchers. The data are there, are available for everyone. Please use them. We would like your feedback, your advice, and your collaboration. And it will be nice to give us your feedback and to discuss with you whatever you want. And with that, I would like to thank you again for the invitation, for your attention, and my apologies for this technical problem with the laser pointer. Thank you very much.
Thank you, Antonis. The usual question from me. As a user of ground-based data for validating MIDAS, do you have any requirement, any requests for the data not being
Personally, I would like to have more observations about spectral signals coming on video, because I use it to discriminate from the other coarse particles, which is marine particles. it will be very, very useful, because I see a lot of validation studies, they are using only the action exponent along with AOD, which is okay, it's accepted as a measure, but you cannot avoid the mixing with other coarse particles. And for this reason, in my case, I use the harmonic retrievals, knowing at the beginning that I will lose a lot of data compared with the sun direct measurements. But this was a penalty, but I said that this is what I'm going to do here.
Okay, thank you, Antonis. Other questions? Yes, Marie-Lisa? The mic is there.
Thanks a lot. So thanks for presenting it all together, putting it all together. I had a question about the beginning of this whole process, the MERA2 data set. Do you have any plans to change it to a higher spatial resolution step?
This is a very nice question. Actually, we are using the default. We are making the assumption that within this grid, the dust load does not vary. It's not true, everybody knows, but when we have a long dominant transport, we can accept this. The only way that we can think so far, but there is a lot of computational cost, is to perform a downscaling to these values, and then to go to the spatial resolution of the MIDAS dataset at 0.1 spatial degree, or to regrade the data from the MIDAS to lose the spatial resolution that we have, the default data, and to go to MERAP. This is maybe, I don't know which of them. I would suggest, and I would like the first one, but I know that
I was going to say the first one for sure. You don't want to go to 50.
There is a lot of computational cost for this. This is a problem.
That is true. I was just wondering, why was it for historical reasons that you picked MERA to start this whole? Because it's been many years that you've been working on this data set.
Yes, we can apply it also with CAMs, with other data sets.
Exactly.
In Ridley et al., they use 4 models. But I think that MERA CAMs, or both of them, if you make a combined product, I don't know if you can have, it will be better. But again, it's now we are focusing on expanding the data set and including the Terra. Because in all these things that you see behind, there is a lot of processing, a lot of things, and we need a lot of time and all this. But the code is there, we can change the input, so we can test whatever we want, and this will be also a nice exercise, I think. I agree with you.
Thank you.
Thank you very much for your question.
Other questions or for people online? No? Then thank you again, Antonis, and thank you to all the speakers of this afternoon, this morning, the whole day.
Join the action, join the newsletter. Follow us on social media for news and announcement.